our topic for today is section 4.3, which is combinations. So, what kind of configuration is that? It might be a good idea to somehow compare it with what we did at the end of section 4.2. In section 4.2, we did P&R, and that was the count when we have n elements, no repetitions, not everybody is in, just R of them, but order is important. Now, for combinations, and the symbol will be CNR, it's somewhat similar. Repetitions, no. Is everybody in? Then no. Is order important? No. So what do I mean when order is not important? When we choose elements, then we don't care how they are lined up. Usually we line them up in one order, like natural order, but then all the other orders are discarded and they are not counted. And formula for CNR, let me write the formula, that's a theorem. So CNR, it's a theorem. Uh, 4.3.1 says the following: CNR. There is the other symbol that's very often, it's called choose symbol. And why it's called choose? Because out of n object we choose R, and only the choice is important. So who's in and not how they are ordered. And what would it be? Formula says the following: is the same as P and R, but we divide it by R factorial. So if you recall the formula about P and R, condensed version n factorial over n minus R factorial, that was P and R, but done with an extra R factorial, this is the formula. So, two goals here in the beginning of the section. One is to explain why are we dividing by R factorial, and the other one is to see how do we count them and then how do we apply them. So for example, let's get example. We have 4 letters, A, B, C, D. We choose 3 of them. So is order important or not? Let's see first if order is important, like P and R. What do? We do it lexicographically. So these A is ahead of B and ahead of C. So A, B, C comes first. And then what else? So starting with A, then we can go what? A, B, D. You always replace the least important digit. So it's A, B, D, then what else? A, C, B, A, C, D, and then A, D, and A, D, C. So with A in front, we just shuffle. First we choose B, C, but both in B, C and C, B order, then B, D in both order, and C, D in both orders. That's with A in front. What about with B in front? The same story. So B, now we go what? B, A, C, B, A, D, and that's, we have now to change A, so it's B, C, A, B, C, D, B, D, A, B, D, C. Then with C in front, so it's C, A, B, C, A, D, C, B, A, C, B, D, C, D, A, C, D, B. Initial line has 6 of them. And finally with D in front, D, A, B, D, A, C, D, B, C. No, DBA, sorry, first, so DBC. It's good to write them in order so that we don't lose some of them. So I always, when I hit the wall with the last digit, then I change the one in front of it for one step. So here I hit C, which is the last digit possible, and then I increase A to B. And start from the bottom, increase when I hit the wall, which is C here. I stop, then I go DCA and DCB. So how many is this? That's 34, which is 4. Why is that? 4 times 3 times 2, as we said, 1, 2, 3, and that would be 24. But now what? That's as permutations in PNR. In CNR, we only think about the content. So this guy, ACB, and whoever doesn't have D actually, so BAC, BCA, CAB, and CBA, all these guys have the same material, same content. Who's in there? A, B, and C. How are they lined up? Oh, we don't care. And so, all these 6 actually will be reported as only 1. How do I report it? In which order doesn't matter, but psychologically it's better to report them as this one. Doesn't matter, as I said. We report them as a set, actually. We report just one set, A, B, C. So in the set, you don't care who's in there and the order, although I always write them in the natural alphabetical order. Who else is there? Let's see, A, B, and D. So that's 1. Then whoever has A, D, B with the same content, that's the same one. I should have 6 of them, D, A, B, and then, if this was a live class, I would ask for, no, it's 6, that's it, A, B, D. And I said I write them as a set. When you have a set, that's not as a word. In the word order is important. When I write them as a set, just the content is important. Then the second combination. So one combination, second, no matter what the order, was the third one. Let's see, a blue one. Blue one would be ACD, ADC, CDA, DAC, CAD. Do I have 6? One more, DCA. Here it is. There are 6 of them that looks like A, C, B. And the last one, I'm going to circle those that were left, and that's what? BC. So I only have 4 of them. Just 4 configurations. And actually that's exactly, here explains why do we divide by R factorial. Because here we divide, so it was 24. But I divided by 3 factorial. Why? Because all these shufflings within A, B, and C count as only 1. So I have 6 3 factorial shufflings. But so if I want to count them as 1, I need to divide. So I get 4. So hopefully that explains this formula. What else? How do we calculate actually combination? So let me see example. What if I have 9, choose 3 to calculate? By the way, calculators also do that. They have a command for this. But if you do it by hand, here's the way how I suggest that you... first, let me write it the way I explain it up there, but then I will do the shortcut. So, like the last one, it says 9 factorial over 3 factorial times 6 factorial, because R is 3 and then minus R is 6. But here's what happened. There was lots of cancellation, and generally if you think of it ahead of time, you can save in calculation process. 3 factorial, I'll keep 3 factorial, but the 6 factorial, I'll put 6, 5, 4, 3, 2, 1. And then what happens? I cancel 6, 5, 4, 3, 2, 1, cancel 6, 5, 4, 3, 2, 1, and here is the rule you can use when you calculate combination. On the bottom, you write 3 factorial. So you write 3, 2, 1. And on top, you write the same sequence of the same length, but starting with 9. So it's 9, 8, 7. You see, 3 up, 3 down. But here start from 3 to 1, here from 9, as long as it takes. And this is the combination. But by the way, it's always divisible. So, so if I cancel 3 and here, 1 and 4, I'll get 3 times 4 is 12, times 7 is 84. The numbers are much smaller than permutations. All right. There are two more big things in this lecture. One is to recognize combinations within a text so that you know that people very often mix up those. And the question is always, is the order important? And you need to learn how to recognize that within a text. And then combinations as numerical expression have some nice properties, and I'd like to analyze them and to tell you about that. But let me first recognize a couple of configurations so that we know how to use the formula. I'll leave the formula so that we have a reference. So here it is, example 432. Example 432, it says the following. 1. Team of 4 members to be chosen out of 11 people. In how many ways can we do that? I'm doing a little shorter sentence, you have completed. And then little restriction, suppose 2 persons insist on working together on a team. In how many ways can you choose it? Let me warn you, problems from this section could be quite tricky because they are word problems. And you easily make an expression, so nothing warns you that your answer is not correct. General number expressions look nice, you multiply numbers, you get some results. Very often in mathematics, when you're on the wrong path, somehow that heavy calculation warns you that something is not going the right way. Here, nothing warns you, so you have to be very careful with the way you set it up. So here's a solution, part I. So we are choosing 4 out of 11. Repetition, no one can occupy 2 places on the team. Is everybody in? No. My question is order important or not? What do I mean? What are we asking? Who's on the team, or is he first member of the team, second? No, they're all members of the team. So if they all have equal roles, then it's not important, are you chosen as a first or as a fourth? The only thing is who's chosen, so order not important. That's it. Now we know that that's what? C 11,4, and that's 11,4. That's 11 times 10 times 9 times 8, 4 numbers. 4 times 3 times 2. Well, I think 4 and 2 is 8, cancels, 1, 3. 3 times 11, 33 times 10, 330. So there are 330 possible teams. Second one. I don't know, sometimes problem is that texts, when you say it in real life language, are not that precise as mathematics would like it to be. So it might be that this is not, so suppose 2 persons insist on working together. What do we mean when we say insist? So they say, if one goes, the other one goes. They don't insist that they are both on a team. They just say, if you choose one of them, you have to choose both of them, like twins or something. So what happens then? Then what do we say? We cannot just call the formula. You have to adjust your formula. We say, we have 2 cases. What are they? Both on, both in, or both out. That's what it means that they insist on being together. And then it's easy. If they are both in, that means what? 2 spots are already taken, no freedom there. So they are in the team, so your only freedom is now you have 2 seats on a team, and you have how many members to choose of? 2 of them are in already, so you have C, 9, 2. So among the remaining 9 members, you need to assemble the other 2 spots, and that's it. And that would be 9 times 8 over 2 times 1, which is 36. You can say, wait a minute, but why did we choose them first? Why don't we choose? When do you choose them? We said it's irrelevant. So we always, on combinations, we choose those that are tricky to control, and then those that have no restrictions, they are just chosen later on. If they are both out, that means all 4 spots are available. But now what? If they are both out, that means they are not on the list anymore. For those teams, we just remove them from the list. So I now have 11 people. I have still 9 people, but now they all 9 compete for 4 spots. So 9 times 8 times 7 times 6, 4 times 3 times 2, again 4 to cancel 8, 3 cancels 2, so that's what, 63 times 2, which is 126. Do I add them up? Yes. Why? Could it be? Because it's OR cases. Or, is there an overlap? Can the same team have them in and out? No, of course. So there's no overlap. There's no team that belongs to both categories, so I will add them up. So when I add them up, I get what? 162. That's the answer. I want to say in my group. Oops, I just noticed that what since the knowledge. I didn't do the problem that's there. There is an error in my notes. I just saw that. I'm gonna do 9-3 there. I just did a problem where there are 9 players and 3 are chosen. And this was 11-5. That has nothing to do with the problem that's there. Sorry, I have to adjust this problem. Solution has nothing to do with the text. I probably changed the text. I forgot to change solution. All right, one more example. This example is very often asked in both probability courses, in our course. You can see it very often. It's fairly simple, but one needs to understand the structure. What would then be example? 4, 3, 4. Let me take the note of the error so that I know. Correct. So example 4, 3, 3, what does it say? It says the following. A club has 5 men and 4 women. And they say, how many distinct, we are choosing group of 3. But those of 3 that have exactly 1 woman. And then in part 2, it says how many teams have a group of 3? At least 1 woman. So see, first you need to understand the text between exactly and at least. So solution, here you cannot just call the formula. That would be the worst way to go through this section and chapter, to just call formulas. Let's hope one of them will hit the problem. So you need to adjust it until you recognize configuration from the formula. So what happens here? If I'm choosing a group of 3 that has exactly 1 woman, that means actually choice among women and men have no interference. So I can break this into 2 subroutines, or 2 stages, or 2 steps. So here it is. On one side, like in one room, I choose men. In one room, I choose women. And then whatever I get, I assemble the team, whatever these guys give me, and whatever these women give me, their choices, I'll just put them on the same list, and I will get my team. So that tells me, since I'm combining the pieces, I'm sure that at the end I'll put times, not plus, times. Why? Because it's not or. Because if it was or, so I can either send men or women. No, I need to send them both. None of them is complete team. They both give me the pieces, male piece and female piece of the team. So, and then they are assembled together, and that's what we said in the product principle. So what happens about the men? There are 5 men. How many spots? 2, because 1 is for women. So I have C5, 2, which is what? 5 times 4 over 2, which is 10. For women, it is C41, which is just 4. You can choose it in 4 different ways. So there are 10 choices for men, 4 choices for women. The answer is 10 times 4. You remember that 3 from section 4.1. For every choice of men, it branches into 4 choices, which women will be added to that list, or the other way around, of course. So here is the answer is in 4 different ways. All right, and then part 2 is different because they say at least 1 woman. But and you need to understand precisely what does it mean at least 1. At least 1 means 1 woman, or 2 women on a team, or 3 women on a team. And there's no overlap, so I can do plus between them. Now we have alternative. So there are full committees. Committee is completed, and I say, oh, there's 1 woman there. Or there is other, so I'm not assembling to make product through. And here it's alternative. So I do all the count where there's only 1 woman, those with 2, with all 3. I said, each of you are acceptable. Those with 1 woman, that's exactly what we calculated. So among men 5, 2, among women 4, 1, so that's 40. What about 2 women? Then what? Here I have C5, 1. So now men the same way. Choose 1 out of 5. Women chose 4 out of 2. And then 3 women is C4, 3. For men, nothing, no choice at all. Just when women send the candidate. And then just calculation, what would that be? 40 plus. This is 5, this is 6. 4 choose 2 is 4 times 3 over 2, which is 6. So this is 5 times 6. 4 choose 3 is just, among 4 women, I choose 3. Okay, let me do C4, 3. We'll see a quick way to calculate this, but right now we are not ready for that yet. 4 times 3 times 2, when it cancels, it's just 4. So altogether 40, 30, 70, 74. Here it is. That's the answer. So what was instructive in this example? That we actually had a nice interplay between product principle and addition principle, and then we were able to look at combinations where we broke the things in the particular points. All right. So what else? Oh, here's a very interesting problem. 434. There is a little trick there. Hi, sorry for sudden interruption. It was just my battery went out. So on the finish of that problem about yes, choice of committees, so we actually had on the bottom of the page here 40 for 1 choice, then we had 30 for the choice with 2 women on the committee, and with 3 women on the committee we have 4. We just add them up, and the result was 74. So that was just the part that was cut out, right? So that that you have the end of that problem recorded. All right. Now I'd like to show you one more example that is somewhat confusing if you just look at it carelessly. And that's example 434. How many strings? How many beat strings? So 0 ones. Bit strings of length 10 contain exactly 3 ones. So 3 ones and 7 zeros. So what's a little bit confusing in this problem is that when you have a string 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, just if you look at it carelessly, one would say, wait a minute, order is important for a string because there are zeros and ones. So order is important. It's important if I put 1 here or I put 1 here. But basically, we have tons of repetitions here, so we cannot use our CNR formula or PNR formula because order is important. One would say it should be PNR. But basically, there are tons of repetitions here, so you cannot call any of our formulas. Actually, if you rephrase the question, then the answer comes very easy. Answer is very easy. So what? I need to put 3 ones. Where do I put them? Wherever I want. I need to choose 3 spots to put ones, like these 3. When I make that choice, that's it. Configuration is there. I put ones there, zeros everywhere, and that's it. So my only goal in this construction, my only design is choose 3 out of 10. Who gets chosen first? Doesn't matter. In all of them I put 1, no matter if I choose this first and then this. So order is not important. I'm choosing out of 10 spots. I choose which 3 will host ones. And the order is not important. Who was among them chosen first. So that's C10-3, and then that's C10-9-8, 3-2-1. So that's what, 120. So that's how it works. So you need to phrase it properly, and then it will come again. Let's do one problem, and then we'll make a little theorem about it. And this example says the following. Example. In how many ways? Can we reorder the letters of the word hullabaloo? So what's happening? None of our configurations works because there are repetitions. And let's count those repetitions because that will be crucial. So it will be 3 L's. 1, 2, 3. There are 3 A's, I think. No. Who else? There are 3 L's. No, there are 2 A's. Okay. There are 2 O's. And these are the only repetitions. H, U, and V are just regular, just repeating ones. Altogether 10. 3, 2, 5, 7, 3, 10. That's exactly what it is. So here's the solution. I will pretend that those L's are different. So I'll make them maybe in different colors. One blue, one green, one green, and one red. So now they are kind of 3 different letters. I do the same with A's and with O's. So what would that be? I would get 10 factorial. Why? Because I have 10 different objects and I can shuffle them in 10 factorial ways. But then what? Every permutation of L's, when I change red comes here, blue comes here, green is actually not changing my configuration because on black and white printer, black and white sees it as the same word. So how many of those permutations among L's can I do? 3 factorial. So I have to divide because I have 6 repetitions of each word because of different ways I shuffle L's. The same thing for O's, so times 2 factorial. The same thing for A, 2 factorial. That's it. And actually, so that's the n equals, that's a number. To have complete sentence, and here's the theorem. What's the name? Theorem 432. So suppose that we are rearranging the list of n objects consisting of n1 occurrences of object 1 n2 of object 2 and k of object k. In this theorem they are allowed also to be ones, so I would count h here and b as well, although 1 factorial is 1, we never count that. So n1 plus n2 plus nk is n. So each of those appearances, that's the total number of letters. Then we call that p, n, n1, nk. As I said, ones in that list are here, but we don't usually write them, is n factorial over n1 factorial, n2 factorial, and k factorial. That's exactly what we concluded here. All right, that finishes the combinatorial aspect of this section. And now we want to go to the properties of combinations. And they are important for a few reasons. First, they help us to calculate them faster. They are used in other areas of mathematics. For us, particularly, they are important because we'll use them in section 4.4. So, properties of combination. Property 1. N choose R equals N choose N minus R. What's this? So first, why would we care? That's always the most important question. Why are we better when we know this rule? Number 2 is what is the meaning, and then configure combinatorially, and then what is the just rigorous proof. So here's why is this property 1, prop 1. Important, here's for what? Suppose I need to calculate 7, choose 5. And generally I can write it. How did I tell you to do that? 5, 4, 3, 2, 1. Here's 7, 6, 5, 4, 3. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Balanced. But then what happens? 5, 4, 3 cancel. And actually I get this. 7 times 6 over 2 times 1, which is basically what? 7 just 2. 5 and 2 are complementary with respect to 7, so which one I use doesn't matter. Of course, smaller one is better. So instead of 7, 5, I should have known immediately that I can use 7, 2 and get it much quicker. Why is this logical? Why is it logical that this is correct? Because here it is. If I have 7 people in the room, and I need to choose 5 to be in, on the team, on the bus, whatever. What about it's the same thing as among those 7 people, choose those 2 that are out. Because once I choose who is out, everybody else is in. So those that are out, I can choose 7, choose 2 ways. Those that are in, 7, choose 5, but those are determining the same stories. Once I know who's in, then I immediately know who's out and the other way around. That's why the number of configurations is the same. Calculationally, what would be the proof? What? n choose r by definition is n factorial, r factorial, n minus r factorial. What is n choose n minus r? Basically the same thing, but now r, because r came first, now n minus r comes first. And then I go n minus r. But that n minus r is just r. So I get n factorial over n minus r factorial, just in different order. So the same thing, just in different order. So that's what I said a minute ago. In, out, and this is out, in, the same story. All right, that's the first property. Second property is just something to be aware of so that you're not confused. It's very simple. I'll put it here on the side, property 2. N choose 0 is 1, and n choose 1 is just n. Just write the form. So this one is just n over 1, because just one member, that's very easy. Combinatorially, if I have n people and I choose 1, I can choose either one of them in n different ways. This might be a little trickier. Why? Because what is n choose 0? Calculation, it's n factorial over 0 factorial, n minus 0 factorial. N minus 0 is just n, so these cancel. But how much is 0 factorial? Maybe I never told you that. 0 factorial is 1. That's by math convention. Convention of mathematicians, the 0 factorial is 1. So this is 1. So that was very simple. Combinatorially, I have 10 people. I need to choose nobody to go on the bus. So in how many ways can this story be executed? One way, just nobody gets on the bus goes empty, that's it, that is the story. So how many configurations? One configuration. All right, and now the most famous property among all the properties of combinations, and that is Pascal identity. We need that for our section forward, and we'll use it very nicely, but let me put it on the board. Pascal identity. It says the following: n choose r plus n choose r plus 1 equals n plus 1 over r plus 1. What's this telling us? In next section, when we build Pascal triangle, you will see even nicer how this looks geometrically. But generally what it says, that here we have n objects. So here we choose r of them, here we choose r plus 1 of them. Total of those two counts is the same as one count, where we have n plus 1 object and choose r plus 1. There's no reason in the world to see this really happening, or maybe there is, I'm not obvious, not very simple one like the previous ones, but it's really true, and we will see that calculation. So proof. Crucial idea will be something that I mentioned in the previous section, and that is, if I have like r plus 1 factorial, that's r plus 1 times r minus 1, 3, 2, 1. But this is actually r factorial. So r plus 1 factorial can be, I start making factorial, all the others are still kind of boxed in that construction. So here it is, my left side equals. I use definition, n factorial over r factorial, n minus r factorial. By the way, this a few times I asked for this proof as a problem on the exam. And n factorial r plus 1 factorial times n minus r minus 1 factorial. And there we go. I just want to add these two fractions building common denominator. And here is how I'll do it. Let me here you see here is r factorial, here is r plus 1 factorial. This guy has an extra member, so let me split that. So n factorial, r factorial, plus n factorial. Using this property, I will write r plus 1 factorial as r plus 1 times r factorial. The same way here, this guy has an early start, has an extra member with respect to this one. So I write it using the same property as n minus r times n minus r minus 1 factorial. Because this is the number preceding n minus r minus 1, the same way as r plus 1 precedes r. And I lost my n minus r minus 1 factorial. When you look at these numbers, this is the same as this. This is the same as this. These two guys are now the same. So what do I do? Common denominator. This guy needs r plus 1, so I'll put r plus 1 on the bottom. And on top. This guy needs n minus r, so I put n minus r on top, and n minus r on the bottom. So that's just basic algebra. That's it, we are done. Just a little, algebra, but everything is there. So basically now they have the same denominator. I will start packing back. So r factorial times r plus 1 is r plus 1 factorial, the same way as we opened it from before. And n minus r times n minus r minus 1 factorial is n minus r factorial. That same disciplines. On top, both guys have n factorial, so I'll factor it out. And who's left? R plus 1 plus n minus 1. And then what? R and R cancel. So what do I have on top? N plus 1 times n, which is n plus 1 factorial. What do I have on the bottom? R plus 1 factorial. And in order to match definition, I will write it as n plus 1 minus r plus 1. 1 and 1 cancel, so they're the same thing. So what's this? I have a number, here I have other number, here is their difference. That's exactly the definition of a choose coefficient, so that will be n plus 1, r plus 1, which is our right side. As I said, I just wanted to have this ready for our next section. In our next section, we will frequently use this very interesting and nice identity. Once again, it's called Pascal identity, and you're probably familiar with Pascal triangle. And this is the crucial identity that supports the structure of that triangle.